Over the past 2 semesters, Team 14 successfully designed and built a modified version of the Arizona Foundation Solutions moisture level system. This system was designed to autonomously remove excess moisture from the soil beneath homes, alleviating problems associated with soil swells and foundational cracks. Two sensors, one located beneath the home and the other located on the home's exterior, communicate with a PLC to operate an exhaust fan based on the relative humidity recorded by the sensors. When the humidity exceeds a predetermined set point, the PLC initiates fan operation, removing unwanted moisture from the soil. At the same time, the PLC uploads the sensor and fan run data to an external website so that AFS can monitor the system remotely. AFS's outline for the system requirements were sensors that provide a humidity reading with an accuracy of plus or minus 2.5%. The new system must be designed for seamless integration with the existing components, and the system must be capable of exporting fan run data for company evaluation. This semester, the team solidified the component selections and then began prototype building and testing. We'll now go to Dan to discuss the results of testing and prototype implementation.
Thanks, Brett. Testing started off with testing the controller's written code or its program. The controller's code was written in blocks. Each block was tested after completion to verify syntax and desired execution of the code. After all blocks of code were completed, the blocks were combined into one complex code. Upon combination of all blocks, the syntax was again verified and the code was uploaded into the controller. The system was then bench tested to verify proper operation of the controller. This was done by taking the system's control switch to manual on and verifying the light turned on and stayed on regardless of humidity. The switch was then taken to manual off, verifying the light turned off and stayed off regardless of humidity. Last, the switch was taken to auto and humidity was brought above the on set point. The light turned on. Humidity was then brought below the offset point. The light turned off. This verified that all control modes operated as expected and that the control relay operated at proper humidity values. After successful bench testing, the system was integrated into AFS's system at AFS's site. The same type of performance test was executed with the exception that AFS's actual fan replaced the light. All control modes were tested and verified again in the same manner as before via AFS's fan. Completion of this test improved to AFS they had a working prototype that was ready for installation in the field. Next, we will go to Allison for our plan on demo day.
Thank you, Dan. Over the past week, the team has been making preparations for demo day. The poster has been finalized and printed. It summarizes the major points from the final report and incorporates more graphics and illustrations to make it more appealing to the observer. The team plans to run the pilot lamp test during the product demonstration since we cannot use the exhaust fan on demo day. Visitors will be shown each of the 3 operating modes and they will also be shown the Cayenne interface. Due to restrictions with ASU Wi-Fi, we will not be able to run the Wi-Fi program that uploads data in real time to Cayenne, but the automation portion of the project will be adequately demonstrated. All of our remote members will be available via Google Hangouts throughout the entire duration of demo day. We are looking forward to a successful final demonstration. I will now turn things over to Ben for a recap of the last 2 semesters.
Team 14 began first semester with the goal of designing a system for AFS that autonomously removes excess moisture from the soil beneath homes, alleviating problems associated with soil swells and foundation cracks. Over the course of the project, the increase in desire for remote monitoring capabilities made this an important design function as well. To achieve these goals, AFS identified several design specs to guide the team's research and development. The team spent most of its first semester researching both the existing system in action as well as industry standard components that would be capable of meeting the desired specifications. The team then presented its preferred design to AFS during a cost-benefit analysis at the end of the semester. Based on feedback received during this meeting, the team had to reevaluate some of its component choices during winter break. This ultimately had an impact on the team's budget and schedule. The team began the semester slightly off schedule, ordering parts a month later than the team had initially planned. Once all the components had arrived, the team began with the coding and preliminary testing of the system. Once the code had been successfully debugged and verified through bench testing, the team performed a startup test using a pilot lamp in lieu of the exhaust fan. After working through some difficulties, the team performed a successful integrated test with the exhaust fan that verified system functionality for all 3 operating modes. The integrated test proved that the system met all of AFS's design criteria and performed all desired functions successfully. The project was successful from this standpoint as well as in its design for economics, manufacturability, and sustainability. In closing, the team is satisfied with the results of prototype testing and is making preparations for a successful final demonstration.